Excel Core Pure, Vectors 3, Equations of Planes, the equation of a plane in Cartesian form. Let's consider the plane which contains the known position vector A and has a normal vector n. A general point on the plane is usually referred to as R. So we can always find the equation of a plane using r dot n equals a dot n. So here, to get to the Cartesian form, we're using x, y, z for our general point, n1, n2, n3 as the normal vector, and when we dot a with n we will get a constant term, here referred to as k. So once we've done the dot product on the left hand side, we have two variations of the equation of a plane in Cartesian form. If you just wanted a simple way of writing the equation of a plane, you could go for the form ax plus by plus cz equals constant k. And note that the coefficients of x, y, z, in this case the a, the b and the c, represent a normal vector to the plane. However, if you're going to use the equation of the plane to find the distance from the origin, for example, you may find it useful to use n1x plus n2y plus n3z plus constant d equals 0. This form of the Cartesian equation is then compatible with the formula that you will find in a formula book. So here, for example, we're going to find the Cartesian equation of the plane that contains the point 1, 2, 0 and is perpendicular to 2, 5, 3. So my normal vector that I'm going to use in this question is 2, 5, 3, and a known point on the plane I'm going to use 1, 2, 0. r dot n equals a dot n defines the plane, and because we're going straight to a Cartesian form, I'm going to use x, y, z for my general point. Dotted with a normal, 2, 5, 3 equals the given point, any given point on the plane, in this case 1, 2, 0, dotted with the same normal vector 2, 5, 3. So the dot product on the left will give me 2x plus 5y plus 3z equals 2 plus 10 plus 0. So we could go for 2x plus 5y plus 3z equals 12. And that is a perfectly good Cartesian equation of the plane. However, if I was now going to go on and find the distance from the origin, for example, I would rearrange this to 2x plus 5y plus 3z minus 12 equals 0, and then I would have an equation of a plane which is compatible with the formulas to be found in your formula book. It's also worth noting that we will end up with the same equation of the plane even if we have a scalar multiple of the normal vector. So for example, if the normal vector was 4i plus 10j plus 6k, then this normal vector here would have twice the magnitude, and so would that normal vector we're using on that side, because we'd be using 4, 10, 6. So when we do our dot products, we would end up with 4x plus 10y plus 6z equals 24, which is of course equivalent to 2x plus 5y plus 3z equals 12. And there's just clarification of the two versions of the plane equation. So in summary, the vector equation of a plane in parametric form is r equals a plus lambda b plus mu c, where lambda and mu are different parameters. A is a given position vector on the plane, and b and c are non-parallel direction vectors on the plane. The vector equation of a plane using the normal can be found using r dot n equals a dot n, or r dot n equals a constant k, where k is the dot product of a with n. The Cartesian equation of a plane can be given as ax plus by plus cz equals k, or n1x plus n2y plus n3z plus d equals 0 if you are going to be using one of the formulas for distance out of a formula book. It's worth noting in both Cartesian forms the coefficients of x, y, z will represent a normal vector to the plane. So in this problem you've got 6 equations of planes given in different formats, and you've got to work out which of the planes are parallel and which ones are identical planes. Parallel planes will have normal vectors which are identical or scalar multiples of each other, and they will not have any common points. Identical planes will have normal vectors which are identical or scalar multiples of each other, but there will be a common point as well. A further challenge for you is, if you know the normal vectors to your planes, can you identify which planes are perpendicular to each other? In the next session we're going to be looking at the angle between two planes.